All right, let's jump right into this explainer. Today, we're looking at a technological arms race that is moving, well, blazingly fast. We're going to explore how the absolute sheer pressure of modern electronic warfare has forced drones to evolve. They aren't just remote-controlled gadgets anymore. They've become these highly resilient, fully autonomous, AI-driven machines. The modern battlefield is basically an electronic fog, and the tech designed to survive it, it's honestly nothing short of incredible.
Which brings us to the big question. What actually happens when a drone loses all connection to its pilot? Because severing that human connection, completely breaking that data link, that is the ultimate goal of electronic warfare today. So what happens when a drone suddenly goes totally blind and deaf in hostile territory? How does it actually finish the job?
Well, here is how we're going to break it all down today. First, we'll look at the electromagnetic fog. Second, edge AI autonomous navigation. Third, terminal AI and decamouflage. Fourth, the rise of fiber optic UAVs. And finally, we'll wrap up with AI swarm synergy. So, Section 1. The electromagnetic fog. Let's look at this invisible war. Traditional drones rely heavily on centralized control and GPS, which, creates a massive single point of failure. If they get jammed, they just fall out of the sky. But modern systems, they abandon that entirely. They use decentralized mesh networks and onboard edge AI to survive. And physically, the internal components are actually protected by military-grade conformal coatings. This shields the delicate electronics from both harsh weather and the extreme thermal heat generated by intense electronic warfare.
And this leads us to a crucial concept, the GNSS-denied environment. Now, we're not just talking about losing a signal like when your phone drops coverage in a tunnel. No, we are talking about zones where GPS and satellite signals are completely drowned out by high-power noise, or even worse, they're digitally spoofed with fake coordinates and timestamps. If a drone's internal algorithms are fed this spoofed data, it can literally be tricked into altering its course, crashing, or just flying straight into an air defense trap.
Section 2. Edge AI autonomous navigation. This is how they actually survive that fog. The first major solution here is visual inertial odometry, or VIO for short. Think of VIO kind of like a hiker navigating through a dense forest by memorizing the positions of specific rocks and trees to correct their internal compass. The drone's camera acts as the eyes, extracting visual features from the ground below, while the IMU, the inertial measurement unit, acts as the inner ear, feeling the acceleration. By mathematically fusing these two inputs, the drone can navigate without a single drop of GPS, keeping its positional drift to under 1.5% of its total flight distance. It's wild.
But VIO isn't perfect for every single situation. For short-range dynamic environments, sure, it's great. But for long-range, ultra-low altitude flights, we're talking under 25 meters off the ground, drones will actually switch to terrain reference navigation, or TRN. At that ultra-low height, standard satellite maps distort. So instead, TRN uses particle filters to match the 3D structural features of buildings and trees against preloaded digital elevation models right in its memory.
Now, what happens when the battlefield is covered in thick smoke or it's pitch black out? Traditional visual systems are going to completely fail there. To counter this, engineers are deploying deep patch visual odometry. This uses convolutional neural networks, which is advanced deep learning, to understand the global context of an image, rather than just geometric points. So even in extreme degraded environments like heavy smoke or dust, this AI maintains a staggering 86.1% tracking success rate.
Moving on to Section 3, terminal AI and decamouflage. This is when the man is totally out of the loop.
This is achieved through automatic target recognition. Running on highly efficient edge computing boards like the NVIDIA Jetson Orin, the drone analyzes its video feed at 5 frames per second. And to handle the massive power demands of this processing without melting down, these boards utilize advanced silicon carbide and gallium nitride power electronics. The drone autonomously extracts features to identify tanks or radars, draws a pixel-level bounding box, and then, completely without human input, initiates the final terminal dive.
Of course, militaries are constantly trying to counter AI targeting. A really common tactic is painting vehicles with high-contrast zebra-like stripes to create geometric distortion, confusing standard optical cameras. But the AI, it evolved right back with a decamouflage system using a dual validation mechanism. It cross-references its confused optical view with a thermal view. Because hey, you can paint a tank like a zebra, but you absolutely cannot hide the massive thermal signature of its engine block. The AI locks onto that heat and strikes.
Section 4. The rise of fiber optic UAVs. This is essentially the ultimate physical hack.
These drones actually carry literal spools containing 10 to 20 kilometers of hair-thin glass or polymer fiber cable. As they fly along, they unspool the wire. Because they transmit data via light pulses down this physical tether, rather than using radio waves, they are 100% immune to all electronic jamming and GPS spoofing. They emit zero radio frequency signature, making them totally invisible to enemy scanners, all while providing the pilot with unjammable, zero-latency, high-def video.
But as you might guess, this physical tether comes with some major drawbacks. Flying a drone trailing 20 kilometers of string means it can easily snag on trees. Plus, dropping miles of undegradable polymer is creating a pretty severe environmental plastic crisis. Also, engineers discovered a wildly unexpected problem. The dense spool of wire left inside the drone was acting as a physical dampener, literally absorbing the drone's own explosive blast. They actually had to invent fragmentation shielding to separate the spool from the warhead so the energy directs outward like it's supposed to.
Which brings us to our final part, Section 5, AI Swarm Synergy. This is the era of decentralized warfare.
Drones are no longer just acting as lone wolves. They're forming decentralized swarms, sharing real-time threat data with each other. A key tactic here is sending in waves of incredibly cheap decoys, costing under $10,000 a pop. Manufacturers achieve this low cost using SLS 3D printing and lightweight thermoplastic continuous carbon fiber composites. These decoys simulate the radar cross-section of dangerous strike drones, forcing the enemy to turn on their radars and waste multi-million-dollar missiles on plastic and foam. This perfectly exposes their positions for the real strike drones trailing right behind.
This entire cat-and-mouse game boils down to a strict mathematical model of survivability. Kill probability equals susceptibility multiplied by vulnerability. Basically, to survive, the swarm has to constantly adapt to reduce its susceptibility, meaning how easily it gets detected by radar or cameras, and reduce its vulnerability, meaning how easily a hit actually brings it down.
And this leads to perhaps the most chilling aspect of modern swarms, the adaptive routing loop. In this architecture, a destroyed drone isn't a failure, it's high-value data. The exact moment a decoy is intercepted and destroyed, the AI instantly captures the enemy radar signal and location, calculating the exact blind spots in the defense network. Within milliseconds, it reroutes all subsequent drone waves to flow perfectly through those newly discovered gaps, just like water flowing around a rock in a stream.
A quote from Euromaidan Press perfectly summarizes the core philosophy driving this rapid, unprecedented evolution. The human is in the loop when possible, and out of the loop when electronic warfare makes it necessary. The chaotic environment demanded autonomy, and the engineering simply delivered it.
Which leaves us with a profound question to end this explainer on. As these machines continue to learn how to survive, navigate, and strike entirely on their own, literally feeding on their own destruction to dynamically evolve their tactics in real time, how will fully autonomous swarms redefine the very future of global security? Because it's a reality that's already here, flying right through the electromagnetic fog. Thanks for joining me as we unpacked this incredible source material today. Keep questioning, keep learning, and I'll catch you on the next one.